This is the last topic that we're going to be covering in stoichiometry. Uh, so after this, you guys won't have to worry about it anymore. But this one does kind of bring everything that we've done together into one kind of type of problem that we're going to be working on. So what this last topic is called percent yield. All right. So before we get into percent yield, I wanted to talk about experimental versus theoretical yield. So far, all of these calculations that we've been doing to find limiting reagents and how much product you can make with a certain amount of reactants and all that, that's all been to find what's called theoretical yield. So anything that we calculate straight on paper is going to be a theoretical yield. It's not what we've actually measured in a laboratory, right? When we do the reactions in real life, the results, they're hardly ever going to match up exactly with what the math says they should be. All right, and there's all kinds of reasons that can be. It could be because your starting reactants weren't as pure as you thought they were, or because when you stirred it, some of it stuck to your stirring rod, um, or when you transferred it between containers, you didn't get all of it, or I mean, there's tons of other, hundreds of other small sources of error like that that you can run into. So when you measure something in the lab, it's not going to ever exactly match what it should be. All right, but that value measured in the lab after you do a reaction in real life is called the experimental or the actual yield. Okay, and what we're talking about today is called percent yield. So the way that you find percent yield is to take the experimental yield divided by the theoretical yield times 100. And that will tell you how close you got to what the actual value should have been based on the math. All right. So when I was doing chemistry labs in college, a lot of times our labs were graded on our percent yield. So if you messed up one step in the reaction and you lost a bunch of your reactants, and you came and at the end you weighed it out and you only had like a 55% yield because you lost half your reactants when you broke a beaker or something, then the highest grade you could get for that lab was a 55, and it ruined some people's grades. I'm not going to do that to y'all, but that is kind of something to be careful of when we do labs from now on. You want to make sure that you're not losing any of your reactant to stuff like that, and keeping it as close to the theoretical yield as you possibly can. Okay, so the way these problems are going to look is that they're kind of going to be all-in-one problems, where you're using all of the skills that we've been working on these last 2 weeks to find the percent yield given a set of data. All right, so this first problem here, it tells you that 29 grams of CaOH2 and 16 grams of hydrochloric acid are allowed to react. If the result of that reaction is 18.5 grams of the CaCl2 being produced, it wants you to find the percent yield. Right? And so for each of these problems, there's going to be a set of steps that you follow. The first one is just going to be balancing the reaction. So that's pretty straightforward. You've done stuff like that for 2 weeks. But if we look here, we have 1 calcium on the left, 1 calcium over here on the, 1 calcium over here on the right, 2 chlorines on the left, 1 chlorine on the right. I got those backwards, sorry. 2 chlorines on the right, only 1 on the left. And then the hydrogens are not matching up either, and neither are the oxygens. So to balance this reaction, we've got to set up our little chart. All right, so we have reactants and products. And the elements that we're worried about are calcium, oxygen, hydrogen, and chlorine. Okay, so we've got 1 calcium there and 1 there. We've got 2 oxygens on the left and only 1 oxygen on the right. We've got a total of 3 hydrogens on the left, and 2 of them on the right, and then 1 chlorine on the left and 2 of those on the right. So to balance this out, I say we start with oxygens, just going down the list. If we have 2 of them on the left and only 1 of them over on the right, then we can go in there. Oh, let me bring that back up for y'all. We can go in here to our coefficient in front of where our 1 oxygen is and change it to a 2. So we've got CaOH2 plus HCl. I didn't leave myself enough room. Let's try that again. Okay, we can come in here in front of our H2O and change that to a 2. So that gives us a total of 2 oxygens. And it also changes our hydrogen total to be 4. Alright, and then we can balance the other ones out by changing this coefficient in front of the HCl to a 2. That gives us a total of 1, 2, 3, 4 hydrogens on the left. And it also gives us 2 chlorines. So we've got everything balanced out there. So this is our balanced reaction. That's 1 step down. Okay, second step is to determine the limiting reagent. So that's what we were working on yesterday. So if this is giving us our quantities in grams, the first thing to determine limiting reagent that we have to do is transform them into moles. So we can come down here and say we've got 29 grams of this one and 16 grams of this one, and we need to transform those both into moles. So to do that, we need to find the molar mass of these 2 compounds here. So let's come up here, kind of out of the way, and see if we can figure out the molar mass of our CaOH2. So calcium, if you look on the periodic table, weighs 40, oxygens weigh 16, and hydrogens weigh 1 each. We've got 1 calcium, 2 oxygens, and 2 hydrogens in our molecule there. So altogether that's 40, 32, and 2. So those all add up to a total of 74 grams per mole. And then with the HCl, our other molecule, hydrogens are 1, chlorines are 35, and there's only 1 of each of those in that molecule. So we can just add those together to get 36 grams per mole. Okay, once we know our molar masses, to convert to moles, we divide the mass here by the molar mass. So we're going to take 29 divided by 74. All right, and that gives us 0.39 moles. And then we're going to take 16 divided by 36, and that gives us 0.44 moles. Okay. So now that we know how many moles of each of these we have, we can determine which one is the limiting reagent by just picking one of them and solving for the other, basically, with the mole ratio. So let's just pick this one here on the left, our calcium. And if we do that, our ratio of our coefficients is going to be 1 to 2, right? Because calcium doesn't have a coefficient in front of it, so that's just 1. So we're going to say here 1 over 2 is equal to 0.39 over x. When we're doing this, we can just ignore this 0.44 value here until we need to compare it. We're only caring about this one. So 1 times x is x, 2 times 0.39, type that in, comes out as 0.78. So what that tells us is, in order to react with all 0.39 moles of the CaOH2, we would need 0.78 moles of the HCl. We only have 0.44 moles, so we have less than what we need, which makes HCl our limiting reactant. Okay, so that's step 2. We've determined our limiting reactant. Step 3 is to plug that in and solve through in order to figure out what the theoretical yield of this CaCl2 is going to be. So we'll do that by going from moles of our limiting reactant, this 0.44 that we have, to moles of CaCl2 using a mole ratio. So the ratio there is going to be 2/1 because that's what the coefficients are. All right, and we use 0.44 and x. We'll solve this for x. So 2x is equal to 0.44, and then we divide both sides by 2 to cancel it out. X is equal to 0.22 moles of CaCl2. All right, and then your last step to finding theoretical yield is to take the number of moles of your CaCl2 and multiply it by the molar mass. So let's come back up here to the top of the page where we're kind of out of the way. Calcium weighs 40, chlorines weigh 35. We have 2 chlorines and 1 calcium. That's 40 and 70 for a total of 110 grams per mole. And then we multiply 0.22 times 110, and we get a theoretical yield of 24.2 grams. Okay, so up until now, everything that we've just done is everything we were doing yesterday, right? You just didn't know it was called finding the theoretical yield, but it's all the same stuff. The only new step that we're doing today is calculating percent yield based off of theoretical yield and what it tells us we actually got in the problem. So the new stuff for today is actually pretty simple, because all you've got to do is take the actual yield that you got in the problem, which if we go back and look, it says 18.5 grams of CaCl2 are produced. So we're going to take that 18.5, we're going to divide it by the theoretical yield that we calculated, our 24.2, and then multiply by 100, and that will tell us percent yield. So 18.5 divided by 24.2 times 100 gives us 76.45% yield, right? So that would be your answer for this problem, for finding the percent yield. All right, and I'll try and make the next page look a little neater. That one was kind of a mess. All right, so our next example here, we've got 170 grams of zinc sulfide are reacted with 95 grams of oxygen, and 84.3 grams of SO2 are produced. It wants to know... Excuse me. There's a typo in here. Real quick, let me fix that. What we should be calculating is the percent yield. All right, so first off, you've always got to make sure your reaction is balanced. That's always going to be your first step. So if our reaction is zinc sulfide plus O2 yields zinc oxide plus SO2, we've got to set up our chart to balance this. So we've got reactants on one side, products on the other, and we're worried about zinc, sulfur, and oxygen as our 3 elements. Both sides have 1 zinc. Both sides have 1 sulfur. But the left side has 2 oxygens, and the right side has 3 oxygens. Okay, so we've got to come up with some way that we can balance this out to where it's the same on either side. All right, and real quick, the easiest way I can see to make it have an even number over on the right side so that we can actually balance it on the left is to go ahead and put a 2 right here in front of your zinc oxide. Right, now instead of having a single oxygen here, we've got 2 of them, so that makes our number even total. But what that does, and we'll do oxygens at the very end because we have these 3 oxygens here. So once we start changing things, we'll make everything else balance and then do oxygens last. But what this does here when we make this change is it changes our zincs to be a 2 on the product side. So you're going to come back over here, put a 2 in front of this one to make them balanced. But that changes our sulfur to be 2. So we got to come back over here, put a 2 in front of that to balance our sulfur. But that affects our oxygens as well. So now, since oxygens are the last thing to worry about, we'll count them all up. So we have 1, 2, 3, 4, 5, 6 total oxygens on the right side. So to make that balanced, our coefficient right there needs to be a 3, and then we're done. All right, so that one's a little bit of a tricky balance, but you guys have done harder ones before, so it hopefully didn't throw you off too much. All right, and then our second step here is going to be determining the limiting reagent. So if we go back and we look again at what the problem tells us, it says we've got 170 grams of our zinc sulfide and 95 grams of oxygen. All right, so if we're trying to determine limiting reagent, our first step is going to be converting those into moles. So let's see, if we've got zinc and sulfur, we need to find the molar mass of zinc sulfide. And the mass of zinc, if we look over here on our periodic table, zinc has a mass of 65, and sulfur right here has a mass of 32. All right, and then this formula only has 1 of each, so we just add these together, come up with 97 grams per mole. And then for O2, O has a mass of 16, and there are 2 in there, so that's 32 grams per mole. Okay. So to figure out how many moles of each of these we have, we're going to do our division. 170 divided by 97 gives us 1.75 moles, and then 95 divided by 32 gives us 2.97 moles. All right, my paper's kind of getting in the way there. All right, so now we just have to pick one of these, set up a ratio, and compare. So we'll just start with the zinc sulfide, the first one. We can say our ratio is 2 to 3, because those are our coefficients. So we'd have 2 over 3 is equal to 1.75 over x. And then we get 2 times x is 2x equal to 3 times 1.75. And then cancel out the 2. And we should come up with x is equal to 2.625. So if we're comparing this 2.625 to our 2.97, we're going to have more than what we need, right? The 2.97 is higher than what we need. So that means the O2 is in excess, and our zinc sulfide is the limiting reagent. Okay, so we're done with that part. We found our limiting reagent. And now we need to determine our theoretical yield. So the question is asking about SO2, because that's what it tells us we actually found as our product there. So if you look at your coefficients between zinc sulfide and SO2, the ratio ends up being 2/2. And we'll work this out to prove it, but anytime you have coefficients that are the same, like this, 2/2, 1/1, 3/3, whatever, you're going to end up with the exact same number of moles. Right, so I can tell you right now, this is going to end up as 1.75 moles of SO2 being produced. But if we work through the proportion and prove it, we end up with 2x is equal to 2 times 1.75, which is 3.5. And then we cancel out the 2 by dividing both sides by 2. And you end up with x is equal to 1.75. Alright, so you can save yourself some time every now and then by just doing the problem like that and realizing that if the ratio is the same coefficient over itself, it's going to be the same number of moles. But if you don't remember and you work through the problem, it's not a big deal either way. Alright, so that's how many moles of the SO2 we're going to have. We need to multiply that by the molar mass to find the theoretical yield. So S and O. S weighs 32, we set up here, and O weighs 16. That is 1 sulfur and 2 oxygens. So if we add those together, we get a total of 64 grams per mole. And we're going to multiply that by the 1.75. Oops. There we go. And it comes out with a theoretical yield of 112 grams. Okay, your very last step is to find the percent yield. So we're going to take the actual experimental yield that it tells us was produced, the 84.3. We're going to divide it by 112, and we're going to multiply by 100, and that will tell us our percent yield for this problem. So we've got 84.3 divided by 112, and then times 100. And this one comes out, pretty close to the same as the other one. It's 75.27%. Alright, so these problems keep getting longer and longer because we keep adding steps onto them, but this is as long as they're going to get. So if you can handle these, then you're in the clear. Alright, make sure you guys get this finished and finish up with all of the rest of your stoichiometry and limiting reactant stuff, because next week we're going to be having a test over all of it before we move on to a new unit. Alright, let me know if you have any questions.